So let me introduce our first speaker of the afternoon. Peter Meadows is a long-time member of the BAA and the BAA Solar section. He was a keen astronomer who started out as a bright young lad of, still in nappies, I think, from what I remember.
Teenager.
A mere teenager with a pair of binoculars and pencil and paper, like a lot of people do. You still observe using the sun's projection method, and you started recording sunspots in April 1977, I understand. And then you carried on doing that through university. University had a telescope and equipment that you could use, and then the hassle of earning a living got in the way for a while. But you didn't really stop, and since then you've been a keen member of the solar section, still continuing to run and contribute and collate observations and support the director in the running of the technical side of things. And I am given to understand that you have agreed that you are taking on the directorship of the solar section when Lynn stands down.
From August.
From August. So, ladies and gentlemen, a warm welcome for Peter Meadows. Thank you.
Okay, so I'm going to talk about a topic that's going to be in a future paper in the journal, and that's how the sun rotates, and particularly differential rotation. And I'll explain exactly what that is as we go through the talk. So the outline of the talk is going to, after this introduction, I'm going to talk about how to measure the rotation of the sun from your own observations, and then explore that as a function of latitude on the sun. And that leads us to the fact that the sun doesn't rotate at the same rate at all latitudes. Of course, we're observing the sun from the Earth, and that's referred to as the synodic rotation rate or period. And if we want to compare our measurements from different times of the year, we need to convert those to the sidereal rate. And I'll explain how we can do that. And then the other thing we want to do then is to try to fit our measurements to a model, a fairly simple model, to describe how the rotation period changes with latitude. And then I'm going to compare the measurements that I've obtained with other professional results and see how they can compare. And what we will find is that the model doesn't accurately describe the measurements. And I'll propose one method or one property of sunspots that can partially explain that. Then I'll briefly talk about the paper that's coming out and how that led to a student project that took place last summer. And then there'll be a brief summary at the end. And I hope to finish by 4 o'clock. Time for tea. If I can get this to work. Seems to have got stuck. Once I got to about 50, I needed glasses. It's thinking about it. let's start again. Cancel that. Yes, okay, that's working okay now. So as Janice indicated, I've been observing the sun in white light for a long time, and all solar observers try to observe as often as they can. And ideally, you'd want to do it once a day. Well, of course, that's not possible, especially this time of year. And if you do that, you see that the position of sunspots change from day to day, not only in their position, but also their appearance. And a lot of solar observers also observe in hydrogen alpha quite a narrow band in the red part of the spectrum. And in that type of telescope, you can see features that also change from day to day, but they also change over shorter periods of time, and in the case of flares, for example, over the space of a few minutes. So really this talk is to try to encourage observers in the association to measure the positions of sunspots from their drawings or images, and see how they change over time. And so what we will do is, as I mentioned earlier, is we'll determine the rotation period of the sun and see how that changes with time. So I think in all solar talks, there needs to be a warning. I'm sure everyone in the association is fully aware that it's dangerous to look at the sun, even with the naked eye, without proper optical equipment. And you need to be familiar with observing methods as well. And that's where the solar section can help you out if you want to get started in solar observing. So for white light, I use an 80mm refractor, as you can see there on the left. And I've been using that particular telescope since the early 1990s. And I have a custom-made projection box at the bottom end, attached with the eyepiece holder. And from that, I project an image of the sun, as you can see here, and in a bit more detail here. So I have pre-drawn discs, and the idea is you center the sun on the disc, and once you've orientated the projection box, you can then start drawing your sunspots and your sunspot groups. In fact, this 80mm refractor is almost the same size as the 3-inch refractor that's used as the reference for the International Sunspot Number. So for white light, if you want to count sunspots and sunspot groups, you don't need a particularly large telescope. If you want high-resolution images of sunspots or in hydrogen alpha, then obviously the larger aperture is better. And the image on the right is just from a partial eclipse we had a couple of years ago. So these are a couple of drawings that I made a few days ago. These are spaced 2 days apart, and you can see that the sunspots have moved. So for example, this one here has moved and developed into this one here. A new group has appeared here, and this one here is this one over here. So sunspots move from east to west, and because I'm projecting the image, east and west are flipped compared to images that you would take directly. So you bear that in mind as we look at some other images. But you can, as I say, over a period of a couple of days, you can see that the sunspots have moved round, and obviously that gives you an indication of the rotation rate. In this talk and in the journal paper, I've made use of images from SOHO and the Solar Dynamics Observatory satellites. And the main reason for that is I can't observe every day, and I don't have multiple images per day either. So these two satellites are very handy for doing more accurate and more frequent observations of the same sunspot to determine the rotation. So to do that, I've written some software that takes these images, so you can see they're actually flattened. They're referred to as flattened images, whereby the intensity is the same all the way across the photosphere. There's no limb darkening. And what I do is I create a mask of the sunspots, as you can see in this image here in red. So the red is the sunspots, both the penumbra and the umbra. And then once that's been done, I then the software merges them into individual groups. And then once you've got each group, you can then measure its position and its size, and also what's referred to as the Macintosh type, which I'll explain a bit more in a moment. And from those images, you can then produce a table for each observation. So it includes, for example, the latitude and longitude and the area. And then I try to assign it the active region number as well. And you can use this data, you can search it. So, for example, you can search for all groups of a particular type. And I'll explain which type I use. So, to actually measure the rotation, we can measure it in rotation rate, so that's degrees per day, or the period in days. So what we really want is a sunspot that doesn't change in its appearance very much as it goes from the eastern limb round to the western limb. Otherwise, it may have its own proper motion with respect to the photosphere. So in this talk and in the paper, I've taken what's referred to as a H-type group. I'll explain a bit more exactly what H-type sunspots are. You could use a more simpler type of sunspot, an A-type group, but they don't tend to last very long. And we really want a group that's going to progress from east to west. So what we want to do is, the easiest method is just to measure the position of the sunspot with respect to the central meridian, which is the axis of rotation of the sun. And once we've got that in degrees per day, it's quite straightforward to calculate the rotation period, just 360 divided by the rate. So in terms of the Macintosh classification, just have a look at the left-hand column, and that gives the different types of groups. So at the top, we have a single sunspot, or maybe one or two sunspots that don't have any penumbra. It's just an umbra on its own, and that's an A-type group. Then you can get more complicated groups where you've got the second one down is a B-type group. Again, the sunspots don't have any umbra, but they're more stretched out in longitude. And then this is a C-type group where you've got one sunspot that's got a penumbra, so it's a slightly lighter shade of grey around the central umbra. And then sunspots become more complicated. So you've got C, and then you've got D, where you've got basically a bipolar type of group. And then essentially you've then got E and F. And the main difference between those three, D, E, and F, is the extent of the group in longitude, where it's less than 10 degrees, between 10 and 15, and then greater than 15. But at the bottom, you can see an individual sunspot, which is referred to as a H sunspot. So it has an umbra and a penumbra, and it doesn't have any, usually doesn't have any other surrounding sunspots. It doesn't have a pair at the other end, just a single sunspot. And there's a few examples here on the right from earlier on in this cycle. So they just look circular. They don't tend to do very much. They're not that interesting, except for measuring the position. So they don't really do very much as they progress from the east to the west. So what I've got here is an animation of a a few days from last summer, and you can see an example H spot here as it moves from east to west. So it starts here and it moves across. So I'm using an equatorial mount, so you've got north, east, west and south marked on. And then at the top here we've got P, which is the position angle of the rotation of the sun. So for these few days, the rotation axis was almost the same as the north-south rotation. And then you can see other sunspots, but they tend to change from day to day, so they're not ideal for measuring the position. We want a sunspot like this that just doesn't change very much. And the way we can do that is I've got some software called Helio Viewer, which is free to download, which I developed over the last 20 odd years or so. And that reads in, my sunspot drawings, it also reads in images of the full disk of the sun. And it will, then you can place on in blue you can see I've placed on a that long grid. So there's that long grid. There's the equator, 20, 40 and 60 degrees north and south, and then east and west as well. And if you just click on a particular sunspot, so for example here, it then outputs the position of the sunspot, as indicated in these two circles here. So it will output the fact that the latitude is 22 degrees north and its longitude is 173 degrees. So what we want to do is to measure the distance from the central meridian to the position of the sunspot. And we have a simple equation. So the central meridian distance is the longitude of the sunspot minus the longitude of the rotation axis here. And in this example here, it's minus 12 degrees. So east is negative and west is positive. That's a fairly straightforward exercise once you've got your image into or drawing into the software. And then it's just a matter of doing the same exercise for each of your images or drawings. And then you can build up a table as shown on the right. So you've got obviously got your date and the latitude and longitude and then the central meridian distance. So in this example here, it goes from minus 67 to 74 degrees. And you can just simply put that into Excel. And then on the right-hand side, you just plot the central meridian distance versus the day of year, or basically time. So day of year is, so the 1st of January is day 1, today is day 24, and so on throughout the year. So it's quite convenient measure of the date. Obviously, if you you have to take special care when you get to the end of the year, if you wrap between the end of the year and the start of the next year. And then in Excel, if you then fit a straight line, and then the gradient of that line is the rotation rate, so 12.8 degrees per day. As measured from the Earth. And it also gives you a R² value, so it gives you an indication of how good the fit is, and as you can see, it's a pretty good fit. The value of 1 is a perfect fit. So then it's a matter of taking a number of sunspots and performing that exercise. So from my own observations, I've got, 12 or 15 measurements. And so I've plotted on the vertical axis, you've got latitude, and then on the horizontal axis, you've got the rotation rate. And you can see straight away, they don't fit on a straight line, but they change with latitude. So at high latitudes, say plus and minus 30 degrees, you've got a rotation rate of 12.6 degrees per day, whereas near the equator is 13.5 degrees per day. So on the left-hand side, 12.4 corresponds to a rotation period of 29 days, whereas towards the equator, we're talking about 26.5 days. So it's quite a change in the rotation period between the equator and higher latitudes. And here we're only going up to 30 degrees. Occasionally you get sunspots that go up to 40 degrees. So the longitude system that we use is referred to as the Carrington longitude, and that has a fixed rotation period of 27, just over 27 days, which is 13.2 degrees. So it's about here somewhere. So as I mentioned, we need to convert from our rotation rates that we measure from Earth and convert those to a sidereal rate. So in the sketch, if you imagine we've got a sunspot at time t1 indicated by the blue dot, and then on the left-hand side we've got the fixed stars, so we're doing relative to the fixed stars. And then by the time the sunspot has rotated around the sun once, the Earth has obviously moved around the orbit around the sun. So in fact, for the sunspot to get back to the central meridian, it has to go through 360 degrees plus the angle theta. So as you can see at time t2. So it turns out that the sidereal rate, so the sidereal rate being from here around back to here again, is shorter than the synodic rate. And the difference is about 2 days or so. So in fact, the sidereal rotation period is 25.38 degrees, and that's how it's defined. So if you look in the handbook and you look at when a particular rotation starts, it's all based on those 25.38 days. So over the period of a year, we go back so you can see that. So obviously this is just a bit less than a month. So over the year, this angle theta here is 360 degrees. It's a full circle round. And so that corresponds approximately to, let's say, 360 degrees over a year, 265 days, or just less than 1 degree per day. But that assumes that the Earth's orbit is circular, which it isn't, and also assumes that the rotation axis of the Sun is orthogonal to the Earth's orbit, which again, it isn't. There's about 7 degrees difference. But if we just take into account the variation in the Sun-Earth distance, we can get a more accurate value for the difference between the synodic and sidereal periods, as shown in the graph. So obviously this variation here is just exactly mimics the variation in the Earth-Sun distance. If we exclude the fact that the Sun's rotation axis isn't orthogonal to the Earth's, we get an error of less than 0.01 degree, which for our calculations is fine. We don't need to worry about that. So I mentioned it's always handy once you've got your measurements to then try to fit them to a particular model, and the one that's used for solar rotation is shown here. So we've got the rotation rate sidereal is a constant A plus B times the square of the sine of the latitude plus C, and then you've got a fourth power of the sine of the latitude. So A, in fact, is the rotation rate at the equator. Obviously, when the latitude is 0, these two terms are 0. Whereas parameters B and C effectively showing the dependence of the rotation rate on latitude. And it turns out that parameter C is really only important for very high latitudes, 50, 60, 70 degrees or so. But because sunspots are really only between -40 and +40, we can ignore C and set that to 0. And then basically, so if this term is missing, we basically then have an equation of a straight line. So if we plot sine squared of latitude against the rotation rate, we get a straight line. And then from the straight line, we can determine A and B. And this is what I've done with the measurements that I made. So on the left here, we've got the sine of the latitude, so sine squared of latitude in the x-axis, and then y-axis we've got the rotation rate. And then you can fit a straight line, and then from the equation here you can. So A is 14.2 degrees, so days, degrees per day, and then we've got minus 2.58 for the dependence on latitude. So if we then backtrack and then fit using these values here, we can fit our model curve to the data. The first thing you can see is that the data points don't fit perfectly on the curve. There's some variation, and I'll explain about that a bit later on. The point to make, yes, okay. So then, if we use the data from SOHO and these SDO satellites, and you perform the same exercise, on the top here I've selected 53 H-type sunspots from this current cycle, and then fitted the model, and again here. Whereas the ones at the bottom, we've got more data points, so because we're going back to cycle 23 onwards, and we've got 211 sunspots. So more data, but again, with these potentially more accurate measurements from the satellite data, again, we get quite a spread of measurements from the actual curve. And then if we have a look at some published model data, so even going back to Maunder, back in the 1880s and 1890s, and then Newton and Nunn again, that's from 34 to 44, 10 years. If you start searching for papers on rotation, you end up with a whole host of people who have been doing it for a long period of time, the last 100 years or so. So I took an average here of 11 data sets from all sorts of observatories. Some people use isolated sunspots, as I did here. Others use all different types of sunspot groups and just merge them all together. I put this one here in here, so this is based on magnetic features rather than sunspots, and you get a slightly different value compared to the others. And then at the bottom here, so these two are the ones I've just shown you, and these are the couple of ones from the journal paper. So obviously, apart from this one here, which is derived from a different type of rotation, the others tend to lie roughly in the same ballpark. Also want to mention that there's some ESA software, free ESA software called J-HelioViewer. I don't know whether their software came before mine or they pinched my name, I don't know, but so it's a Java-based software which is, I'll show some examples from that. And that's based on this magnetic features rather than sunspots. So if we plot the different models that I showed you, we get a whole series of different curves. This one on the inside here is the magnetic one, so obviously that's a bit different. Whereas all the other ones from all different types of sunspots, they all show the same shape, basically, but the offset on the equator is slightly different. But if we take that and plot the last set of SOHO and SDO measurements, you can see that they spread amongst all the different models. And we don't really appreciate that. When you look at a model in the paper, you think, oh, it's going to be a perfect fit. But when you overlay it with the actual data, it doesn't. And there's a huge amount of spread. So what could be an explanation for that particular spread? So one of the things that so I've used, say, the J Helio viewer to look at a very fine time period for sunspots. This is a group of sunspots that occurs at the beginning of December. And so what you can use the software for is to basically you track the sunspot from the east to the west, and it forms an animation. And if I run the animation, what you can see is the rapid motion of the sunspots over about 10 days. So this is obviously a very active group, and there's a lot going on within that sunspot group. In particular, if you have a look at this sunspot on the left, you can see how that changes appearance. So it starts off quite large, decays, and then moves down and round. So obviously this type of group isn't going to be suitable for measuring the rotation because there's so much going on. So what I then did is I went back and picked 3 of the H-type groups that I selected earlier, and I'd assumed that they didn't do very much, and from day to day they don't appear to do a huge amount. But if we look at them in this animation, you can see that they're moving around a small bit, but they are actually moving around themselves. So I've got 3 examples, and they're all at the same latitude, or very close to the same latitude. So the rotation rate is virtually the same between each 3. And this is the second example. So again, it moves around a little bit, and you may notice a small little sunspot appears halfway through. So that's indicating that there's still some activity within the photosphere. And then the third example is this one here. So, and in this example, it actually starts to decay. So I'm sure if I looked at more examples, you'd find the same sort of thing, that there'd still be a slight motion of the sunspot over the period of a couple of weeks or so. And so you've got some proper motion, even for sunspots that don't appear to change from day to day. So as I mentioned, there's a paper coming out, so it's been accepted for publication. And it basically explains how to measure the rotation rate yourself from your own images or your own drawings, simply just using Excel or some other type of spreadsheet. Not particularly complicated. And for the paper, I've used 24 different H-type sunspots, and it derives the model formula as I showed there. So I also, in the paper, produced a subset of those 9 groups to form a smaller data set that could be used by students as an introduction to the way the sun behaves. And the 9 I've chosen, it gives a model value here, which is almost the same as this one. So after the paper was submitted back in April, May last year, Lynn Smith, director of the solar section, mentioned that Helen Usher of the relatively new education and outreach section was looking for suitable projects for a student pilot project. So I suggested the topic of rotation. And to assist the students and whoever was teaching them, I prepared a student's Excel workbook for those nine sunspots for the students to put their measurements in there, and all the graphs and things would come out automatically. So, as I said, there was a teacher version of this spreadsheet as well with all the expected results. So this is an example of the spreadsheet for one particular sunspot, and basically the students had to fill in the numbers from the software in within the red box, and then the graph would appear, and then they take the slope here and put it into here. And then they obviously did the same for all the 9 different sunspots. Produced a summary sheet, so just the 9 different sunspots and their rotation rates and periods in these, and then display them in the 2 graphs. And then there's a separate tab for the model fitting as well. So again, that's all done for them. And then the actual images themselves were provided in a separate zip file. So you may already be aware that there was a week-long project with students last year run by Helen. And one of the afternoons they performed this particular project using the differential rotation. And I've just taken this from the newsletter from last year. So it turns out that the exercise was challenging. Well, you don't want to make it too easy for students, do you? And it turned out that because a few of them got stuck, they worked together, which is also a very good thing to do. You know, when you start working, you end up by you work with other people. You don't work on your own very much. But they all managed to complete the exercise, and they all managed to demonstrate that the sun rotates in a differential way. So that was good. Okay, so it looks as if that particular project is going to be run again this year, this summer. And this project will form part of that. I think there might be a few tweaks, but I think I might make the instructions a bit clearer, perhaps. But apparently one of the students who read the instructions didn't have any problems. Or maybe I should say probably read the instructions carefully, didn't have any problems. Okay, so just to conclude, so as Janet says, I've been observing for a while, and I like to analyse the drawings or images that I obtain to extract extra information. And obviously one of them is the rotation of the sun. So as I've shown, we need to convert from synodic to sidereal rotation rates to compare measurements taken at different times of the year. And then we can fit those to a fairly standard model that professionals use for differential rotation, and then compare those with other models. So one bit of further work that could be done is to use the rotation rate to try to input that into a physical explanation for differential rotation and help explain why sunspots start at high latitudes at the start of a cycle and then progress towards the equator, towards the end. So as I mentioned, there's a journal paper coming out looking at those H-type sunspots. And obviously part of that formed the pilot project for the students. I should say that the students are typically A-level students. So really I'd like to encourage members, particularly of the solar section, to use their own images, to use the software, the free software, and measure their own differential rotation rates. We have some excellent images within the section who obtain very high resolution, very good quality, full disk images of the sun. And they could equally use the software to extract extra information from their own images. And I'm sure they'd find it an interesting exercise to do, especially this time of year when it's cloudy. Thank you very much.
So have you time for questions?
Yeah.
All I need is a willing victim to run around with the handheld microphone so that people on YouTube can hear you are. Oh, well volunteered, Steve.
Nick can't do it.
Yeah, I'm not going to volunteer today.
Okay. So absolutely fascinating. I mean, you have such technical skill in order to create this. I mean, I'm just in awe of what you can do with it. Did you enjoy the summer school event and putting that work together?
Put it together, yes.
Yeah.
I wasn't involved in the day-to-day one of it.
Yeah.
Yes, putting it together was interesting because it just extended from what was in the paper,
Yeah.
just by chance. It was in the paper.
And have the students that took part, are they still in touch and keeping on with what's going on?
I believe that they're in touch with
Okay. And you're going to do it again this coming summer?
Yes. That's the plan.
Mad glutton for punishment. It's a great way to get, especially A-level students,
Yeah, get involved.
join in. Yeah.
All you need really is Excel. I'm sure all students will Excel at their schools. And the software and the images, and you can, away you go.
Yeah.
Follow the instructions.
Yeah.
And
Get your images up.
yeah,
there.
yeah. So
Excellent.
as far as I'm aware, they found it fascinating to do that.
Yeah, satisfying.
Yes.
Very
yeah.
practical. That's
Exactly,
the thing.
yes.
Practical astronomy.
And as I mentioned, they worked together as well as a team. They worked together as a team to do
And
that.
they hadn't known each other before. They were
I think
what, different schools or something.
there might have been just been one school.
One
I think, I'm not sure.
Because it's quite difficult these days getting in schools, isn't it? With all the permissions and everything.
Yes, yeah.
So well done.
Well, I think all the work was done by Helen and her team.
Well, hopefully she's listening.
Hopefully, yes, somewhere.
I can hear that. Right, ladies and gentlemen, have we any questions from the floor? Sir. Yes, we need them on a microphone because we're live streaming with you.
Of course, yeah. Okay. Well, great talk. Thank you. Fascinating. I'm a bit of a, I would say, an amateur viewer of the sun. I draw it. I do it in hydrogen alpha and white light. I don't know what you think about projection because of optics and heating. And secondly, how do you draw the sunspots on that frame? It looked rather impressive, but it looked difficult to draw on without putting pressure on the telescope and it's on the eyepiece. Sorry, these are basic questions, not about your actual talk.
It's a fairly sturdy projection box. So once I've got the mount, it's an equatorial driven mount. The trick really is to orientate the box so you've got north, south, east, west. And for that, I have the sort of the circle that you saw earlier. And then behind that, I have a second sheet of paper with horizontal east-west lines on it. and then you can see those faintly behind. And then you just, when you don't have the drive on, the drive's off, you then place the sunspot on one of these lines, and then if the sunspot moves across on the line, you know that you're orientated correctly. If it moves up or down, you have to turn the box round so it's orientated correctly. But in terms of putting pressure on the paper, I don't find that a problem. Maybe the thing is I've used it for a long time, so just experience. Yeah, and there are quite a few members I think there are quite a few members in the solar section do it exactly that way. And then you can use that then to determine the number of groups and the number of sunspots and do your various counts. Do you? Okay. Oh, right. Right, okay. Just as good, probably.
And don't anyone be intimidated. That's the whole ethos of why we have our sections, to focus sort of those who've been doing this for longer and have lots of expertise to share. That's what it's about. John Cook from there.
Yeah, do you know if there were any flaring events in the area of the sunspots you were looking at that might disturb the magnetic structure around about in the nearby area?
I didn't look specifically to see whether there were any flares going off at the same time.
So I'm thinking that might move the visible structure that you see.
Yeah, that's right. If I can go back. Can't remember which one it was now. It's, yes, yeah. Yes, it might have been this one here. That you can see there's a sunspot on the left, which isn't the one I used. So I used the one on the right, but you can see that the one on the left is actually moving quite quickly.
There is some activity there, yes.
And if it hadn't gone around the limb of the sun, they may have got very close to each other. And obviously that has an effect on the one on the right as well. If you get another sunspot that gets close to it, it's going to move. So I found producing these little videos quite instructive in terms, because I just assumed that these H groups didn't do anything, but it turns out they potentially can.
Yes.
And so probably what I would have to do is to go through all of them and and try to exclude some that appear to have a high motion, and then derive the model again. Yeah. There's a bit of bias in there, but it might be an interesting exercise.
Jeremy, Professor Shears, sorry. You have a question?
Peter, thanks very much. You mentioned one sunspot affecting the motion and the other one just then. Is that through a physical disturbance between the two sunspots, or is it a magnetic interaction?
I'd have thought it's more of a magnetic. If you imagine, I mean, these H-type groups, all sunspots have a bipolar nature. There's a north magnetic field and the south magnetic field. In these H groups, only one of the polarities is above the surface or near the surface. The other one is deeper down. Right. It's still there, but it doesn't manifest itself in terms of a sunspot.
Okay.
So if you get something else with an opposite magnetic field getting close to that, it could potentially affect it.
And are the magnetic fields of those individual spots measured by any of these instruments? In other words, are there data available that you could use to explore what you're seeing here, to explain what you're seeing here?
So yes, so for the Solar Dynamics Observatory images, there's also an image that's effectively a magnetic field. So there is an image where they form a magnetic image, and where you can see the pluses and the minuses in the image
Around each spot.
and the sunspot itself.
Yeah.
Yeah.
Yeah, yeah,
And so you probably could use that data to
Yeah.
measure the strength of the magnetic field
I see.
and see whether there's anything else around it.
Yeah. Yeah.
In fact, that's probably a better way of doing it than looking at
Yeah.
nearby sunspots. Interesting idea.
Hours of fun ahead of you, I can see
Yes.
that.
Yeah.
I'm only doing this, Steve, so you have to run from one side. I'm not running anywhere.
We wanted to see if you were faster than Nick was at the Christmas meeting. So this is Nick James, Director of the Comment Section.
Yeah, Peter knows that, I think.
But the audience don't talk.
Sorry, yeah. No, I've worked with Peter for quite a while, so we know each other. It's really interesting, the observations, but do we know why the sun behaves like this? Why it's got this differential rotation? Is it something that's inherent in the way stars work, or?
Yeah, basically, yes. I mean, it's the dynamic dynamo effect of the sun. You know, it's all related to the magnetic field.
So it's all related to the generation of the magnetic field. And how deep does it go? How deep does the differential? I mean, presumably it doesn't go all the way to the middle.
I wouldn't have thought so. No, I don't know. I don't know how far it goes down.
Right.
People have measured the rotation rate above the photosphere, looking at the chromosphere and even layers above that, and measure the rotation rate using different types of data, ultraviolet data, for example.
And are they coupled to the photosphere? So is the chromosphere above the photosphere rotating at the same? Yeah. Right.
Well, as you go higher up, the rotation rate changes. It's not the same as on the photosphere.
Right.
So it's a, as you can imagine, it's a very complicated.
Yeah. No, but it's a great project. It's a great project for A-level students because you can get into it by simple observation, but then there's loads of physics questions that you can answer.
Exactly.
Yeah.
How do these things work?
Yeah.
What's the you know, even a sort of a simple bipolar group with a north and south magnetic field, if you get a complicated group, they're going to interact with each other. What do they lead to? Solar flares, for example. Yes, it leads into a lot of physics, complicated physics as well, if you want to go into it.
Yeah, I don't know how you would measure the depth, how far down you'd reach a limit that you couldn't go any further.
Yeah, there are some techniques where you can probe the inside of the sun, but probably not to that fine scale.
Sorry, talk to microphone. I'm getting abuses.
Yeah, so it is a very complicated structure.
Interesting, fascinating. Right, we've
Yeah,
another
I
three
wanted to ask a
questions.
further question, primarily to give our friends some more exercise coming from the other side of the room.
He's not
But
talking yet.
in terms of the differential rotation, is this continuous or is it in belts as you go down up and down in latitude? I mean, is it like on Jupiter, say, where you have more discrete regions, or do you think it's continuous?
So no, you obviously got them going from the high latitude down to the south.
Yeah.
But you get streams of area where it's faster than normal, and then you get other streams where it's slower than normal, and how they interact.
So it is like bands then?
It's like bands. They're not horizontal bands, but they're sort of inclined.
Oh yeah, because
as you go from the north down to the south.
Right.
And it can be the interaction of those zones that can lead to sunspots appearing.
Okay, thank you.
Interesting. Dr. Rushton.
Yeah, in fact, I've just been upstage because my question's just been asked by Jeremy. Jeremy, I was just wondering how the physics a bit varied from the physics of planets' atmospheres rotating, because clearly, I mean, it could be the same and it could be quite different. But, I think
Obviously the sun rotates far slower than, say, Jupiter.
Yes, but
So
the equatorial regions rotate faster than the polar regions, don't they?
They do.
Yeah.
They do. And on Saturn, in fact, all the gas giants. So
that's all it was. So.
I'm getting lazy now.
You remember Alex?
Got sort of a couple of questions. Follow on from this. Is there any differential between basically the movement, as it were, or the yeah, let's call it the movement between north and south. Is there any variation between the differential movement between north and south of the equator line? That's what I should have said.
So as far as it appears, that the northern hemisphere and the southern hemisphere can be treated as separate, and you don't get sunspots going from the southern hemisphere to the northern hemisphere.
Yeah.
Partly because the polarity of sunspots in the northern hemisphere gets reversed for the southern hemisphere. So obviously, if you've got those two trying to interact with each other, that would cause issues. But they are separate, even though sunspots can get very close to the equator with a fraction of a degree,
I think
north and south.
sort of to clarify, is the amount of movement symmetrical either side
Well,
of the equator in terms of speed?
That's an interesting question, because I've in the calculations I've done here, I've assumed that they're the same.
Right, yeah.
But in fact, if you read up on professional papers, they do find a slight asymmetry between the north and the south,
Right.
which varies with time, the time of the cycle and from cycle to cycle. So from the sort of level of detail that I'm doing, yes, you assume it's symmetrical, but in reality it's not. There's a slight asymmetry. So obviously that indicates that there's something slightly different going on in each hemisphere at a particular time. Whether it's related to what activity there is in the sun in each hemisphere. So if you look at sunspots, you get periods when the northern hemisphere is more dominant. There's more groups in the north and the south. Then a few months later, it could change, flip over. So the two hemispheres do behave slightly differently.
A small one. With your helioviewer, do you incorporate the time of day when you actually make the observation?
Yes. Okay. Oh, gone the wrong way.
Hello, you mentioned...
Just finishing answering Alex's question, and then he'll be with you in a second.
Yes, so so the software it depends on what type of data you input. If I already know about the data, it will. So, for example, these are my own drawings, and that's the convention I use for naming the drawing. So it's just D for drawing and the date, and then the software will pick that up and it automatically select the date. I manually have to type in the time. I have to do that myself manually, just by moving your cursor to the arrows and then just going up and down with the arrow keys, and it selects the time. The same with Solar Dynamics data and Soho data. In their file name, it has the date and the time, and the software will automatically extract that and populate the date and the time for you. So I say this data's free. If you go to this address here, so I've got a website, my own website, and you'll find it on there. It's just a simple exe file that you need to download. Nothing too fancy.
Okay, we've got two more questions, and then we've got tea break coming up. So if everyone's okay with that, we'll let you harass Peter during tea break.
That's fine. Yeah,
so long as you let him get his cup of tea first. Okay. So this gentleman. Sorry.
Hello. You mentioned you use a 70mm refractor with image projection and white light. I've imaged the sun in white light, actually through a 150mm refractor, but I've never used projection. I've always taken an image of the sun. Is that of any value?
Yes. So your images that you take, are they of the full sun, the full disk?
Yes.
Yes. So you could import those into the software as well and do the measurements. The only thing is you need to make sure you've got your orientation correct, your north, south, east, west. As long as that's okay, then you'll read in whatever you've got, but in terms of doing the measurements, you need to make sure that your orientation is correct. But yes, no, that's ideal because you get more detail with a 150 millimeter refractor than a
Okay, thank you.
80. So.
And last but not least.
Hello, thank you for that interesting talk. My question relates to the derivation of the rotation rate as it is. So you have a base parameter that refers to your base rotation at the equator. And how was it derived that the second parameter would be related to latitude and the sine squared? That to me seems like, well, how was it derived? And even in the time of Newton and all of these ancient astronomers, yeah, do you know, or did that just came to be through continuous just trying other parameters, trying other functions in that case?
Yeah, I don't know the source of the equation.
Ah, right.
But it's an interesting thing to find out, though, what it is. I
That
don't know.
sounds like a research paper, doesn't it?
Oh, yeah. It must
Maybe you'd
someone.
like to do one.
Yes, someone must have.
Well, I did ordinary differential equations in university and all of that, and the solution to some partial derivatives would involve sine squareds and orders of trigonometric functions. So I guess it's analog of something like that was taking place.
Yeah, I mean, perhaps this comes from fluid dynamics.
Dynamical systems, yes.
Of a sphere, a rotating sphere. I've not looked into.
Not into the maths of it, but yeah.
That's right. Yeah.
Really interesting talk. Thank you.
You're welcome.
Well, I think we'll let you off the hook now, Peter. That was absolutely fascinating. Thank you so much. Okay. And it's always lovely to welcome to our stage practical astronomers with a real...
That was the idea.
Real practical knowledge of what they're doing and expertise.
Yeah, as I said, the idea is that someone who does drawings or images can quite easily do extra analysis for themselves.
Excellent. Well, I think we owe him a large round of applause. Thank you.
No, that's